Okay, so we're just going to start with this one. Question 1 here of 3D.1, okay? And what this is going to be a good, again, a good point of consolidation between what we've been talking about. That is relationships between f of x, f dash of x, and f dash dash of x. So we've got that question over a graph like this, and it wants us to fill this table in. So this one, if you want, you can write down, or you can do it when you get to it. I will just point out as well, we have a good summary table on your notes book, okay, on 3D2, so that's page 40. There's a good summary of what each part describes, and we're probably going to utilise that a little bit to answer this question. Although that's a place where it's summarised, it has all been articulated prior to in the notebook. So we're presented with this graph here, okay, and I'm looking at that and I'm going to go, that's some kind of cubic. I know that because it has 3 roots, so it's going to be a cubic of some variety, okay? All we're asked to do is indicate where is it positive, where is it negative, and where is it 0. So if we're just considering the function, what is the function of x? Those are the y values. So if we look at point A, the y value is positive. If we look at point B, the y value is negative. Point C, positive. Point D, positive. And point E, negative at 0. We're just saying, when is it positive? When is it negative? When is it 0? What's the y value at those points? Okay, now we're going to fill in the f dash of x column. Now remember, f dash of x is the slope. So it's telling us when is it increasing and when is it decreasing. Let's consider at point A, you can look at it, you can see we'd be going downhill. If we were to walk along there, you'd be going downhill. At point A, we have negative slope. Okay, the slope is negative because you would be walking downhill if you were to walk past it. At point B, the slope is 0. It's not going down and it's not going up, the slope is horizontal. And we know that the slope is horizontal at turning points, at local max and local minimum. Okay, so the slope is 0. At point C, right here, we have positive slope. You would be walking up the hill, so positive. At point D, we again have slope of 0. It's a local max. And at point E, we have negative slope. We will be walking downhill past that point. So that's the way to look at the function and see, is it increasing or decreasing at that point? Nothing outrageous there. And then in our third one, what we should remember, the second derivative tells us the points of inflection, and it tells us when a function is concave up, okay, when it's concave up, when it opens upwards, and when it's concave down, okay, and where it changes, that's the point of inflection. And when the second derivative is positive, it's concave up. When the second derivative is negative, it's concave down. Okay, let's look here. Here we can see it's concave up until about point C. Okay, it's concave up over that region, which means the second derivative is positive over this region. Okay, so the second derivative is going to be positive at point A and B because it's concave up at those points. At point C, that's where the point of inflection is because it changes from being concave up to concave down. Now opens downwards. So that's going to be our point of inflection. And point of inflections mean the second derivative is 0. And then we can see over this interval it's concave down. When it's concave down, the second derivative is negative. So points D and E are negative. Okay, so we fill that in, and that's how we should start to think about it. All right, any questions? Very good. So let's move on. We sort of started making our way through 3D.1, and I said to only do question 4. Okay, so now what I'm going to do, I'm going to entertain one of the later ones. We're going to use both our calculator and calculus techniques to solve all of the parts of this one. Firstly, what does it ask us? X squared e to the x. Part A, discuss as x approaches infinity. All right? Positive and negative infinity. As x approaches infinity. So that means as x gets large, what happens to the function? And there's two ways to do this, and you're only going to get one mark here, so you don't have to do it algebraically. The simplest way is to look at the graph. And I'm going to say as x increases, all right, as x gets large, what happens to the y value? And you can see y just increases forever as well. Okay, we can see that from the graph. As x approaches infinity, y approaches infinity. Okay, how can I see that? I can see that because it's going up forever. It doesn't appear to have any asymptote or anything like that. It's just going up. All right, and you can zoom right out and see that characteristic more clearly. Okay, let's explain that one algebraically. Why is it that as x approaches infinity, y approaches infinity? Well, this just means as x gets large. So let's say, what happens as x gets close to 10? If we put in 10 into the function, we're going to have 10 squared times e to the power of 10. So what would that mean? That would mean 100 times 2.7 times 2.7, 10 times, right? It's going to keep going. Yeah, that's going to be a really big number. All right, and then you can think, well, what would happen if x is 100? We're going to have 100 squared, okay, which is 10,000. And then 2.7 times itself 100 times, it's even bigger. So as x gets larger, y gets way larger. All right, so as x approaches infinity, y approaches negative infinity. All right, now let's consider the negative case. All right, as x approaches negative infinity. So if we were to just follow along here on these axes, we can see it's getting closer and closer and closer to 0, although it's never going to reach 0. It's always going to be positive. We have an asymptote there. Let's argue about that. All right, so what we're going to say, this is how we would write it. As x approaches negative infinity, as it gets super negative, y approaches 0, but from the positive direction. Okay, it approaches 0. It's never going to reach 0. It's getting close to 0, and from the positive direction. Okay, let's demonstrate that one mathematically. Let's consider again as x approaches minus 10. Okay, if we've got x approaching minus 10, what we're going to have is minus 10 squared times by e to the minus 10. Okay, now minus 10 squared, that's still going to be positive 100. But over here we're going to have e to the minus 10. We can express that as 1 on e to the power of 10. And we know that that is 1 on e, e times e times e 10 times, so 2.7 times 2.7 times 2.7. It gets really big. Okay, so we have 1 divided by a massive number. All right, this thing here is approaching 0. This is getting closer and closer to 0. And so it doesn't matter how big this number is, any number times 0 is 0. Okay, so it's getting closer and closer to 0. All right, so I've just given an algebraic explanation. If you're like a bit confused, you can just look at the graph. Okay, if you want to talk about this, I'd be very happy to. But it's just considering different parts of the function, what's happening as we get large, as we go that way, and as we go that way, and we can't see it. Anyway, you get one mark. Okay? Part A. Part B. Find f dash of x and draw its sign diagram. Okay, we've got this function here. In order to find the first derivative, we need to use the product rule. We've got u is x squared, u dash is 2x, v is e to the x, and v dash is e to the x. U dash of v plus u dash. Now we want to draw its sign diagram. Okay, so firstly, if we want to draw a sign diagram, we want to know what are the roots. Okay, so when is it going to equal 0? We're going to factorize x e to the x. That's what's common. Okay, factorize there. And now we're going to apply the null factor law. Now, traditionally, when we apply the null factor law, we go a times b equals 0, a is 0, b is 0. Here we've got 3 possible candidates. Okay, so we're going to consider all of them. We've got x is 0, e to the x never equals 0, so we don't need to consider that as a solution. And then the other one is 2 plus x is 0, x is minus 2. Okay, and the null factor law that can extend way beyond 2 products, although that's what we tend to use it for. So we've got 0, that's not a solution. And then this is the other solution. So they're going to be the 2 roots of our first derivative. If I draw the sign diagram of it, it's going to be 0, and it's going to be minus 2. Oh, right, 0 and minus 2. Now, we can get them, we want to know when it's positive, when it's negative. Okay? I've said you're not required to make a manual argument for the sine diagram. So let's talk about two procedures we can use. Okay? The first one that you've been doing a bit is to graph the function. Okay? We graph this function. I'm going to graph it here. We've got the derivative. It's going to be 2x. I'm going to just factorise it. X equals factorise form times 2 plus x. That was the derivative function. Okay? Write that down. 2 plus x. Good. All right. And what you can see is it's above. It's below, and then it's above. Okay, so that's how we can get it. That's one way. All right. The other way is to know these. We found these manually, right? This is what the graph of the original function looks like. Okay, and what we can see is we can see a local max at minus 2, and we know if it's a local max, that means it's increasing and then decreasing. So that means it's increasing and then decreasing. So you don't even have to draw the derivative graph. You can recognize these things from the original. It's decreasing and then increasing. Negative slope and positive slope, about 0. Okay, anyway, there's the sine diagram of the first derivative. So we have successfully answered part B. I'll just label that. All right, part C. Hence, state the coordinates of any stationary points. Stationary points occur when the first derivative is 0. The first derivative is 0 at minus 2 and 0. So we have a local max at x is minus 2. What's the y value when x is minus 2? When x is minus 2, I'm going to put it into the original function. It's going to be 4e to the minus 2. Another way that could be represented is 4 on e squared. Okay, we'll accept either of those. And then we have a local min at x is 0 and y is 0. Okay, we can see it from the graph. We know also when you put x is 0 into the original function, 0 times anything is 0, it's going to be 0. Oh, sorry, I skipped to part, that's D, isn't it? So let's answer part C. When is it increasing, when is it decreasing? It's increasing for values less than minus 2 and larger than 0. So here's part C. Increasing. X is greater than or equal to 0, and x is less than or equal to minus 2. Alright, and even that statement there, you can see that from the original graph. Okay, we can see that it's increasing between minus 2 and 0. If you would walk along, you'd be walking downhill there, and you'd be walking uphill for the rest of the time. Alright, so sorry, that skipped C because done in both. Okay, let's move on to finding the second derivative. Alright, so now we're on to part B. Find the second derivative and draw its sine diagram. So I'm going to write f dash of x here, and I've got two forms that I could choose to differentiate, right? Which, there and there. I'm going to use this one because if I were to do it here, I'm going to have to use the product rule like 3 times. Here, what we can do, I've already differentiated that part. That's what I did first. That was our original function. And so I know if I differentiate that, it goes to this. And so then I just need to work out what this part is. All right, so this is our first derivative, 2x e to the x plus x squared e to the x. And I know the derivative of this already, so I'm just going to focus on this part. We still need to use the product rule. U is 2x, u dash is 2. V is e to the x, v dash is e to the x. So the second derivative then is going to be u dash v plus ub dash plus, and then the derivative of this. I know that the derivative of this is 2x e to the x plus x squared e to the x.
that's the equation of the second derivative. Any questions about that so far? Alright, so if we want to draw the sign diagram of this, we need to find when does it equal 0. So what we have to do, look along for common factors. We've got e to the x is the only thing that's common. So let's pull that out the front. We're going to be left with 2 plus 2x plus 2x plus x squared. Okay. Now if we're trying to solve this, we know e to the x never equals 0, so we can get rid of that. And then we're looking at this, and this is a quadratic, isn't it? It's got x squared plus 4x plus 2 is 0. Now we can't find those roots by factorisation. Okay, I know that because in my head I'm going b squared, 16, take 4ac, 16 take 8 is 8. 8 is not a square number, so we can't solve that by factorisation. So that means if we want the roots, we need to use quadratic formula. Okay, so let's go through and apply quadratic formula here to find the values of x. We'll do it reasonably quickly because we've done ad infinitum. Minus 4 plus or minus the square root of 4 squared is 1 equals 2. And choose 1. 16 take 8. Okay, so if you want any like any tips involved in the simplification there, let me know, but for now I'll leave it like that. And we're drawing the sign diagram, so we've got two solutions. We've got minus 2 plus, minus 2 take root 2, and minus 2 plus root 2. Alright, and we don't know what these, I mean you could calculate it to a few decimal places on your calculator. Here we've got it expressed in exact form, that's quite useful for us. But what we do want to know is when is it concave up and when is it concave down? Okay, so when we look at the original function, right, maybe it might have got sketch it, and I might exaggerate it a little bit so you guys can see what's going on. So there's that peak. This is what it's doing, okay? I have exaggerated it intentionally so that we can clearly see the points of inflection. But we have, over this interval, it's concave up, okay, concave up. Then it's concave down, okay, and then here it changes to be concave up again. So they are the 2 points of inflection we found. We know that this one is minus 2 take root 2, because if you subtract root 2, you're moving further down the x-axis, and this one is the positive, because it's further up. And what we can also see, okay, we can see this from the original function, and we can check from the graph of the second derivative if you want, is that it's concave up, so we know the second derivative is positive over that interval. Then it's concave down, so negative, and then concave up. Okay, so we can see that from the original graph. Alright, the other way to see it is to graph the second derivative. So the second derivative, I'll graph that quickly. E to the x times by x squared plus 4x plus 2. Close the bracket. Okay, so what you can see is positive, it's above the x-axis, it crosses back down at that point, so that's what that value is going to simplify to. Then it's negative, and then it's positive again above that point. Okay, so there's 2 ways that we can get it. Alright, so we've got the sign diagram for the second derivative. We're now ready to answer the questions that are asked for. Hence, find the nature and coordinates of any points of inflection. So I'm not going to find the whole coordinate, we're just going to state the x one, I think, because the y one's going to be quite messy. So we've got when stationary points. They're both non-stationary, alright? They're both non-stationary points of inflection. And we can see that in 2 ways. Firstly, visually, the slope is not horizontal at points of inflection. And the second way is that none of these roots occur on the first derivative. Okay? If they occur on the first and the second derivative, then they're stationary. But because they only occur over here, they're what we call non-stationary. So we have non-stationary point of inflection at x is minus 2 take root 2 and minus 2 plus root 2. Okay, so just be careful because it says state the coordinates right, so that would mean both x and y. But the other thing it says is the nature. The nature. So when we say nature, we mean you need to be specific. Obviously, it's a point of inflection. There's two types of points of inflection, Sam. Non-stationary and stationary. Which one is it? Same with local max and local min. When it says state the nature of the turning points, well, one of them's a local max, one's a local min. Okay, lastly, when is it increasing and decreasing? Sorry. When is it concave up and concave down? Okay, again, we can see from the original function, we've made those statements there. It's concave up when the second derivative is positive. So let's say that, concave up. X is less than minus 2 take root 2, and x is greater than minus 2 plus root 2. And then concave down when the second derivative is negative. So concave down between those 2 points. Okay. And what I might do really quickly is just get the approximate y value of the point of inflection. Let's just do that there. So for this one, it's 0.152. No, it's not. It's about minus 0.6. I'll just minus 0.63, and this one about 0.367. All right. Cool. So, any questions about this part here? This is a long exercise, but we got today's lesson dedicated to it. So, hopefully we've sort of gone okay with A and B and C catching up there. But we'll float around, see how we're all doing. Ask any questions.